In this short animation, we're going to look at what oxidation states are, how to assign them, and how they can be useful. So we're going to start off by looking at a simple equation. We're going to consider magnesium reacting with oxygen. It's going to give a white, bright glow, and we can see we form magnesium oxide. Now it's really obvious in this case that our magnesium is being oxidized because it's reacting with oxygen. So it's forming its oxide. It's very, very obvious that it's being oxidized. And because oxidation and reduction always happen together, so it's obvious that the oxygen must at the same time be being reduced. Now, because it's an ionic substance, and you can see the magnesium's 2 plus and the oxygen's 2 minus, we can easily break it up into half equations to show what's happening with the electrons. So the magnesium is going from elemental magnesium to magnesium 2 plus. So I can see it must be losing electrons. So we can write magnesium 2 plus plus 2 electrons. We can see that it is losing electrons. And we know that oxidation is loss. So therefore it must be being oxidized, as we've previously said. Fairly obvious because it's reacting with oxygen. Okay, if we look at the half equation for the oxygen, so we've got our half O2, and it's turning into O2 minus, the oxide ion. So to go from being a half O2 to being the oxide ion, it must gain 2 electrons. So we know that reduction is gain. So we can remember oil rig, reduction is gain. And therefore we know that our oxygen is being reduced. So if we consider another reaction, where this time we're going to take carbon and oxygen, and we're going to make carbon dioxide. Now, it's fairly obvious again that this is oxidation. We've got carbons reacting with oxygen, but because we've made a covalent substance at the end, the carbon dioxide is covalent, it doesn't have ions. We can see, carbon's being oxidized. The oxygen must, in turn, be being reduced because that's what happens in oxidation reactions. Oxidation only happens with reduction at the same time. But because it's covalent, I can't write any half equations, and therefore I need another way of being able to describe what's going on in terms of oxidation. I can't just talk about it being electrons being lost and gained because I'm not forming any ions. So yeah, we can't form half equations for this, so how do we describe what's happening? And that's where oxidation states come in. So next we're going to look at the rules for assigning oxidation states. Now these sound quite difficult, but actually once you get your head round them and you practice, like anything else in chemistry, you practice it, the rules actually make perfect sense. So the first rule is that for simple ionic substances, or for simple ions, the oxidation state is equal to the charge on the ion. So, for example, if something's in group 1 and you know it's only ever going to form a +1 charge, or a 1 plus charge, you know that its oxidation state is going to be +1. If something is in group 2, so say magnesium or calcium, you know it's always going to have a 2 plus charge, therefore its oxidation state is always going to be +2. Aluminium is in group 3, it only ever forms aluminium 3 plus, therefore its oxidation state is always going to be +3. Fluoride is a halogen, it's in group 7, it always forms an F minus ion, so a fluoride ion. The only halogen in there that does do this is always going to be -1. Okay, if we then look at our second rule, so if something is an element, for elements, the oxidation state is always 0. So the first thing you should be doing is looking at your substance and going, is this a compound or is it an element? It doesn't have to be in its standard state, but if it's on its own, it's just an element, then the oxidation state is 0. So O2 is 0. If it was O3, ozone, that would also be 0. If it's bromine, Br2, 0. You get the idea. It could be phosphorus, so P4, or sulfur, S8. Doesn't matter how many of them are in there. If it's an element and it's not part of a compound, its oxidation state is 0. Okay, our third rule then. So the total of all the oxidation states in a compound or in a ion is going to add up to the charge on the ion. So if you've got a neutral compound, the total of all the oxidation states adds up to 0. But if you've got a polyatomic ion, something like sulfate, SO42-, then the oxidation states of the sulfur and the 4 oxygens are all going to add up to the 2-. Okay, so most things, when we're talking neutral compounds, they're going to add up to 0, or they're going to add up to the charge on the ion. Now, the fourth rule only really comes into play when you've got more complicated species that have got a mixture of non-metallic elements joined together. So, and in which case you always need to assume that the most electronegative of the elements is the one that is the negative one. So fluorine always trumps everything else, oxygen next. But we'll have a look at some examples of that. And the fifth rule, this gets you through doing most of your oxidation states, is that hydrogen is pretty much always +1, unless it's in a hydride, which is where a hydrogen is directly attached to a metal, in which case it would be -1 because the metal would be positive. And oxygen is pretty much always -2, unless it's in a peroxide, in which case it would be -1. So you just need to look out for those exceptions. Okay, so now it's time to look at some examples of assigning oxidation states. I'll try and start off with some really simple substances, and then we'll move through into some slightly more complicated ones. As I said before, the more of these you do, the easier they get. So if we consider sodium chloride, sodium's in group 1, so is going to have a +1, so it'll be an Na+, so it'll have a +1 oxidation state. And chloride is going to be -1 because they've got to add up to 0. Carbon dioxide, each of the oxygens is -2, so oxygen is almost always -2, so I've got 2 lots of -2, they add up to -4. The whole thing is neutral, so therefore the carbon must be +4. Okay, if we consider sulfuric acid, so what do we know? We know that hydrogen is always +1, and I've got 2 of those, so that adds up to +2. I've got 4 oxygens, and that's always -2, so I add up my 4 -2s is -8. And the difference between, and the whole thing's got to be neutral, so to get from +2 to -8, the sulfur must be +6. If we look at a chlorate ion, okay, we know that each of the oxygens is -2, so I've got 3 of those, that adds up to -6. The whole thing is no longer neutral, it's got to add up to a negative charge, so I've got to go from -6 up to -1, so the chlorine must be +5. And then if I look at potassium dichromate, so C2Cr2O7, now I know that each of the potassiums is, because potassium is in group 1, is going to be +1. And I know that each one of those oxygen is always -2, so that's all going to add up, lots and lots of -2, 7 of them is going to add up to -14. The whole thing overall is neutral, so if the potassiums are +2 and the oxygens add up to -14, the difference between those is going to be +12. So I know that the 2 chromiums have got to add up to +12. There's 2 of them, so I've got to divide the +12 by 2 to get that each chromium is +6. So finally, let's have a look at how oxidation states are useful, what can we do with them, and how do they give us information about what's happening in terms of redox. So if we go back to looking at the equation we looked at near the start, where we said that carbon reacts with oxygen and forms carbon dioxide, if we assign oxidation states to everything, we know that, so we're assigning oxidation states. The carbon and the oxygen at the start are both elements, so the carbon is oxidation state 0, as is the oxygen. If we look at the carbon dioxide, oxygen's always -2, in a compound and carbon is always +4. So then if we consider how the oxidation state has changed during the progress of the reaction, the carbon has gone from 0 to +4. So its oxidation state has increased. And if the oxidation state increases during a reaction, then it follows that that species is being oxidized. Okay, and then if I look at the oxygen, during the reaction, it's going from oxidation state 0 to oxidation state -2. If the oxidation state decreases during a reaction, then it's a sign that the species is being reduced.